Hello, so welcome to this new chapter that is called diagonalization. What is that? So first of all, let's be clear about something. We're going to work with square matrices. So some matrix A with A is going to be assumed to have n rows and n columns. And we will see that in many cases, well, not always, but it's often going to be the case, we will be able to decompose A the following way. P times D times P minus 1. So what do we have here? The important thing here is that that central matrix D is assumed to be a diagonal matrix, okay? And why would we want that? We want this because diagonal matrices are good. We can do many things much easier when, of course, the matrix is diagonal. And we will see some examples of applications of this in order to solve some differential systems of the first order, for instance. Okay, but really, this is as it is written in those lecture notes. It's really a very central process to linear algebra, and there are many applications of this. I've cited some of them. Well, the PageRank algorithm used by Google in order to order the pages of the results is based on diagonalization. Well, the concept linked to diagonalization, image compression, face recognition, all these algorithms in some kind of way use diagonalization. Okay, so differential system solving. So it's really a very important way to express a matrix. I would say that the previous decompositions that we have studied, the LU and CR decomposition, I really introduced them because they help us understand how matrices work and what's important, what are the fundamental spaces linked to the matrices. But this decomposition is really very important in terms of application, this one. Okay, so which is called the diagonalization. Why are diagonal matrices likable? Let's see. Okay, let's see. Let's consider simple cases. So let's assume I am in R2. Okay, this is R2. So this is the plane with some unit vector I, so the Cartesian in the Cartesian frame, unit vector J. These are the usual denominations. Okay, X and Y. So let's say I've got some point, let's call this point M, with coordinates X and Y, all right? X and Y. Okay, let's assume that I want to write the transformation that takes any point X, Y in R2 and gives you something like 2X minus Y. 2X minus Y, okay? So it goes from R2 to R2. And it takes xy and it gives you something. So for instance, in our example, so I'm going to have 1 2 3 4, so 1 2 3 4 x, and I take the opposite of y, so that would be the image. Let's call that m prime. Okay, if I've got m, this is m prime, right? How would you write? You know a way to write this transformation now, don't you? We can use matrices to write this transformation. Okay, so what kind of matrix can I use? I can just say, well, this is going to be the matrix A, such that A applied to xy gives me 2x negative y. Okay, so what kind of matrix do we want? This is going to be the matrix with 2 0 0 negative 1, right? Xy 2x negative 1. Okay, so this matrix is really a 2 2 matrix. All right, so what's nice about this is that actually I know that so it's very easy to compute even visually the image of any point of the plane by this matrix. You just double the x coordinate and you take the opposite of the y coordinate. Okay, so it's very, very easy. Let's see some other nice things about this matrix. This matrix takes any, let's see what it does to the vector I. The vector I, it's going to transform it into, well, I double the x coordinate, so that's going to land here, and subtract the y, but I have no y. So that vector I is going to be sent in that vector I prime. Okay, can you see a generalization of this? If I take any other thing that is going to be collinear to the vector I, what is going to be the effect of this matrix on this vector? Okay, so let's say this is V. What is going to happen? It's going to be, so the coordinates of V are actually -2 and 0. So if I apply this matrix, the coordinates of the image are going to be, well, -4 and 0. So that will give me the V prime. So what's interesting about this is that anything that is collinear to I, of course, anything that is collinear to I is just going to be have coordinates k and 0. So the effect of this matrix on anything collinear to the I vector is going to be 2k 0. I just multiply by 2 the original vector. Okay, so anything on this line is, so the vector corresponding to anything on this x line is going to be sent to another collinear vector, to this one, right? It's just going to be sent to 2 times itself. Okay, very similarly, what's happening to anything that belongs to let's say the y-axis. Okay, so let's look at the effect on J, on the J vector. On the J vector, so the J vector has coordinates 0, 1. So by the matrix A, it's just going to be sent to 0, -1. So the J prime would be here. Okay, and similarly, if I take, well, 2 times the J vector, this one, okay, with coordinates 0, 2, it's going to be sent to 0, -2. Okay, so that would be my second V2, so V2 prime, all right? So what's happening to anything that is written like 0, k, all right? Something that would be collinear to the J vector, 2, 0, 0, -2. It's going to be sent to 0 and -k, which I can also write as -1 times 0k. All right, so what do we see here? Okay, you see appearing those values that are on the diagonal. You see that they appear here. All right, so, well, it seems very trivial with this diagonal matrix, but then you understand that the action of this matrix is going to be, I'm going to scale by a factor of 2 anything that corresponds to the x-axis, and I'm going to send to its opposite anything that belongs to the y-axis. So you could describe the action of this matrix exactly using those kind of words, right? That's just enough to say its action on those vectors is going to be that, and that's just what you need to know in order to understand what this matrix does. Okay, so that was very easy because the matrix was diagonal. But what's happening now if I want to build a matrix? So let me draw again some sorry about this, some axis. All right, so another plane, so let's write it here. Okay, so what if I wanted to describe, well, or to do something, I want the transformation that is going to multiply by 2 anything collinear, not to the I vector, so that's I and J, not to the I vector, but let's say what I want is this vector. This is going to be my V1 vector, and I want it to multiply by 2 anything that is collinear to that vector, and take the opposite of anything collinear to, well, let's take another one, maybe this one, okay? So let's call that V2, right? So that I want that my transformation, my mapping takes this one, well, it's going to take it here, okay? And anything collinear to that vector, so anything on that line, should be sent to 2 times itself. So if I take this one, this point, it should be sent to that one. Okay, very similar to the other one, except that instead of getting the original ij direction, I want some other directions. All right, and let's say that my first direction is going to be that one, and my second direction would be this one, okay? And but very similarly to the previous one, I would like that anything collinear to this, well, anything happening on that line should be sent to its opposite, right? So this one should be sent here, right? For instance, that would be the image of V2. So you see, instead of having the nice, neat action on the previous, using the original coordinates ij in the Cartesian frame, I would like the same kind of thing happening, but in relative to those vectors. How would we describe this? So maybe you remember that one of the first, very first exercises we did together was find the matrix for change of variables, change of basis. Okay, so the idea, just very briefly, I don't want to do a class on change of basis because maybe we will rather talk about this during second semester. But here, just to explain to you, um, you know that in order to describe the change of basis, so because this is really what I would like to do. I would like to, if I've given something in terms of ij coordinates, I want to be able to express it as something relative to the v1 v2 vector. Okay, so instead of having the original Cartesian coordinates, okay, instead of relying on the original Cartesian coordinates, I want to say, well, actually my vector OM is that's x prime times the vector v1 and y prime times the vector v2. Then I will know exactly how to apply the mapping that I want to this vector. I just have to multiply x prime by 2, and the y prime will be minus y prime. Okay, but in order to have those new coordinates, I have to apply some change of basis matrix. Okay, all right, and so I would apply my change of basis matrix, and let's denote that that is actually going to be the p minus 1. Okay, well, you see, if I change, let's say that p is going to be the matrix that expresses the change of basis from new coordinates to old coordinates. And so if you remember, we briefly talked about this for the again, the very first exercise of the semester. If you want to do the contrary, you will apply p minus 1. So let's say that you would first apply the change of basis for Cartesian coordinates to my new coordinates expressed with the v1, v2 frame. Okay, and then first thing, then you would apply your diagonal stuff. That tells you I'm going to multiply by 2 the first coordinates, and I want and I want to take the opposite of the second coordinate. Okay, but then you want to be able to express the result in the Cartesian frame because this is really the most convenient thing you want to do. And so you apply p to go back to Cartesian coordinates. Okay, so that's why we want the corresponding matrix to this transformation, if I want to express this using the Cartesian coordinates, because this is really what I want, what I have in as descriptions of points in my plane, I will have to first apply p minus 1, then the d, then the p. Okay, so this is basically what diagonalization is doing. It's going to give you the right change of basis in order to see your matrix as a pure diagonal matrix, and then take you back to your Cartesian coordinates so that you can act on your vectors described with their usual Cartesian coordinate. And so if you are wondering what this matrix actually looks like, this is what we really have. So the D is going to be 2, 0, 0, negative 1. The P, if you remember, is just going to be constituted of, well, that's the passage from new coordinates to old coordinates. So the columns of this matrix are going to be the coordinates are my vectors, and my vectors are the v1 is the 2, 1 vector, and the v2 is the 2, 3 vector. Okay, and p minus 1, I've computed that in advance, and that would be 3 over 4, negative 1 over 2, minus 1 over 4, and 1 over 2. Okay, and if you do the complete product, you're going to get 1 over 4 times 14, negative 12, 9, negative 10. Okay, so this is a pretty complicated matrix, and although what its action is very simple if you look at it uh, using the right way. I mean, if you take the right angle of view, which means looking at this matrix but using a change of basis, this is going to be a very simple diagonal matrix that is going to act. And you can check that if you apply this to my v1 vector, which was 2, 1, if you apply this to this v1 vector, you get 14 times 2, 28, minus 12, that's going to make 16, divided by 4, that's going to be 4. And for the first coordinate, second coordinates, 2 times 9 is 18, minus 10, negative 8, plus 8, divided by 4, that's going to be 2. And this is really what we expected, 2 times vector 2, 1. Okay, and you got the same kind of thing if you apply the second vector v2 with coordinates 2, 3 to this matrix. Okay, so that's for the introduction of the concept, and then we're going to work on the definition and generalization of this.